Crazy. We are in Chapter 3. This is 3.1a, and this is called Polynomial Functions and Models. Everything we've done up to this point has basically been a polynomial function, and it's pretty much just for the sake of explanation so you don't freak out on this new word. It's basically just a function like this, or it could be anything up to that. Okay, that's a polynomial function. It's just any polynomial that is equal to an f of x, which means it's a function. So there's some things that go on with polynomial functions, and let's just look at this one right here. When you have it in descending order, 3, 2, 1, and then no variable at all, you have a couple vocabulary words that we need to look at. First one is called a leading coefficient, and that's the number that's in the very front here. Okay, that is, I mean, let's go ahead and put a 3 or a 6 there, just so you have a leading coefficient. So that's our leading coefficient. The degree of the polynomial is the degree of the highest term, or the exponent. So the degree of this would be 3. The leading term would be, I'm sorry, this is the leading constant. The 6 is the leading constant. The leading term is this whole thing right here. 6x cubed is the leading term. The 6 would be the leading constant, or the coefficient. The degree we just went over would be 3. And I think that's pretty much it as far as that is concerned. And given this equation here, there's a whole bunch of stuff that we can get out of that. So let's look at a quadratic function real quick. Okay, so let's go ahead and factor it down into two binomials, x, x, and then we have a 3 and a 1, plus and minus. Alright, so let's look at the zeros. Remember, the zeros is basically the answer, where it crosses the x-axis. So if this is a parabola, it crosses here and it crosses here, which is, zeros here would be 3 and negative 1. That tells me where it crosses. So there's my negative 1 and there's my 3. Okay, so zeros, or again we also call them roots, but basically it's just the answers. The zeros mean when f of x is 0, when the y value is 0, which is where it crosses the x-axis. So that's where that comes from. We also know our x-intercepts are going to be the same as our zeros, but we're going to put those as negative 1, 0, and 3, 0. Okay, so what we do is we take our roots and we put them as our x term, and then our y terms, and will always be 0. Okay, because they're the zeros. Alright, so there's my x-intercept. My y-intercept then will be where it crosses the y-axis, and the y-intercept will always be this last number that's by itself. Didn't I tell you a while back that I'd show you how to find the y-intercept pretty easy? When it's written in this form, descending order, the last number without an exponent is going to be where it crosses the y-axis. So right here is 1, 2, 3, right there at negative 3. Okay, so that's the y-intercept. The minimum value is going to be at negative 4 at x equals 1. So it's going to be right there, and remember you use the negative b over 2a and the f of negative b over 2a in order to find that point, negative 4, actually it's 1, negative 4. So if you took and put your coefficients here, 1, negative 2, negative 3 in here, let's see what we get. negative 2 over 2 times 1 equals 2 over 2 equals 1. And that's where we got our first term. Now you take that 1 and plug it in here. 1 squared minus 2 is negative 1 minus 3 is negative 4. That's where this negative 4 came from. So therefore it makes it easy for us to find our minimum or maximum. There is no maximum. Next we want to look at is the domain. Domain again is left and right. Okay? Left, it goes into infinity. Right, because this keeps going more and more and more to the right. Okay, over forever, and to the left forever. So our domain is negative infinity to positive infinity, rounded. And our range then of this is going to be how high it goes and how low it goes. Okay, so we always start at the bottom, and it goes down to negative 4, right? So we put, and it can be negative 4, so we box that, and it goes up to positive forever. Okay, so that's the range of that. Alright, so that gives us zeros, x-intercept, y-intercept, min, max, domain, and range just from looking at the graph and looking at the equation there. Okay, let's look at one more. Alright, so rather than me drawing everything, we're going to use this cubic function, bottom of page 255, and look at this. So here's the equation right there, and then they simplified it there. Alright, which doesn't really matter if it's simplified for what we're doing a whole lot, except it does tell us what our zeros are. So our zeros are what makes this 0, and this 0. Because this is cubed, it means that there's 3 zeros, there's 3 answers, so it crosses there, there, and again there. So all 3 of those points. X-intercepts, you just take your zeros and follow it with a 0. Okay, and that tells you where it crosses, the exact point. Y-intercept will be, again, the original equation, this negative 12 here, so that's where it crosses, clear down here, negative 12, and a 0's in front there to show that it goes left or right 0 and down 12. Relative minimum, relative maximum. Because this thing is not a parabola, it does, because it's a cube, it does kind of a weird thing. It gets a maximum relative to the graph that we see right here, because obviously this is not a max because this continues to go up. But we're only looking at this part right here, what's relative to the graph. And the relative min is right there. Okay, so the relative minimum is at 1.4, and the relative maximum is at negative 2.7. Okay, over 2.7, up 12.6. And we will get into how to find relative minimum and maximum later on. We're just showing you where they're at. The domain, left to right, infinity. Range goes down forever, goes up forever, so negative, positive, infinity there. Alright, so let's go and continue on here on page 256. Okay, so just have a picture taken of some polynomial functions. So we've got a parabola, a line, and then some other kind of different graphs. And this just shows you, a parabola has an x squared, this shape has an x cubed, this shape has an x to the 4th, and then we've got some absolute values, radicals, fractional exponents, and then we've got fractions here. Okay, so different types of polynomial functions. And one of the things that you'll notice about all of these polynomial functions is they are considered continuous. Okay, that does not look very good, does it? Let's write it so that you can read it. Continuous, which means that when you are looking at them, there is no bump, there's no break, there's not an open circle here for a point that doesn't occur. It's smooth, there's nothing sharp and pointy like we see here And here, you know, it's just all nice and smooth and pretty, and everything works together very nicely. If we had a graph that looked like, well, let me get rid of this, and we had, you know, graph that went here, open circle, and then closed circle this way. I mean, see all the breaks there is in this graph? That's discontinuous. Or even if I had something like, let's see, get rid of some of this here. If I had a graph that was a parabola, but there was an open circle here for a point that didn't work on the graph, that would also be discontinuous. So that's the thing that's nice about polynomial functions, is they're nice and smooth and curvy rather than any pointiness and yucky stuff there. Alright, so let's go to the leading term test. The behavior of the graph of a polynomial function becomes very large or very small and is referred to as the end behavior of the graph. So, for instance, we have a graph here, and we have our parabola. Now, there's a certain point where this thing goes, this thing on both sides goes on forever. It goes this way forever and this way forever. All right? Very important to know that we come into some very important patterns if we look at the end behavior of these graphs. All right, so let's look at bottom of page 257 for even and odd degrees. And before I go into that, let me say that the leading term of a polynomial function, so 3x cubed plus 2x squared plus 4x minus 1 equals f of x. Okay, that's the leading term. Okay, that determines what goes on at both ends of the polynomial function. So let's again look at some even and odd degree polynomial functions and see what we can see. Okay, so notice what's going on here. When the leading function, or the leading term is even, doesn't matter what the number is in front of it. If the leading term, this is not written correctly, that should be negative x to the 10th minus x plus 1, but the leading term, if the exponent is even, look what it does. It kind of makes the same kind of shape here. Now when we make them odd, like start 3, 5, 7, and 9, look, they all kind of look, they have the same shape. Notice this one goes up this way, but this one basically is flipped over across the y-axis because of the negative sign. This also is that shape because of the negative, but notice this one, which has a positive leading term, and this one that has a positive leading term are the same shape going the same way. These are the same shape, just flipped, and that's why, because of the negatives here. Okay. Let's see, anything else? This one opens up because it's positive. This one opens up because it's positive. This is negative, so it opens down. And this one here has a negative x to the 10th, so it opens down. So just some things there that you can see. But let's look at what's called the leading term test. And we'll go into details on that leading term test on 3.1b as in boy.